Good morning, guys. Just finishing my pumpkin spice latte. Okay, now that I've had the sip, we're going to do sections 5.1 and 5.2, which is going to include all of the following: the first derivative test, finding absolute extrema, vertical motion, points of inflection, and using the second derivative test with some examples. So, in section 5.1, we started off with critical numbers. And critical numbers, remember, occur when the graph of the derivative equals 0 or is undefined at some point c, x equals c. They're the zeros on the graph of the derivative graph. They're called critical points on the graph of f, which would be the point c, and then f evaluated at c. So this is the input, that's the output. And all you have to do to find critical numbers is set f prime equal to 0. We'll find f prime and then set it equal to 0 and then solve for x. Okay, so one of the applications in this section was using the first derivative test. And again, I'm listing the steps. You find the derivative, you set it equal to 0 to find the critical numbers. You put those critical numbers on a number line in ascending order from smallest to largest. You choose test points to the left and the right of each of those critical numbers or zeros. And then you plug those test points into the derivative to find the sign of the derivative. We want to know, is the derivative positive or negative? And then write the signs in each subinterval on that number line for f prime, because the sign of f prime tells us what the graph of f is doing, right? So over to the side here, I didn't pre-write this, but I'm going to do it now. Remember that when f is increasing, then the derivative is positively valued. When f is decreasing, then we know the derivative is negatively valued, right? So that's what we're going to use to tell what the graph of f is doing. Okay, when f prime changes from positive to negative, then we're going to have a relative maximum on the graph of f at that x value. And when it changes from negative to positive, we will have a relative or local minimum on the graph of f at that x value. So I believe this is the same example, the first example I did in class. You're given a function. So we want to find where the relative extrema on the graph of f is if we don't have a calculator. So we take the derivative, which is right here, pretty easy. I factored out a 12, set the derivative equal to 0, got rid of the 12 altogether, and then I can factor those by grouping. And remember, if that bothers you, I'll get another color here. So you notice right here where it's just negative x plus 1, I put plus and then negative, the same exact thing in the parentheses. And then it's easier to see that if you factor out a negative 1, which I did here, then negative 1 times negative x gives me a positive x. And if I factor out a negative 1 from a positive 1, I get a negative 1. And the reason I want to do that is because I want to make those the same, so I can factor that out here and then rewrite what's left, which would be x squared minus, and there's a 1 here that we usually don't include, but that's a 1. So now I can set each one of these factors equal to 0, and of course we get, actually you could write this as x minus 1 quantity squared times x plus 1. I mean, if you solve each one of those, you don't do that because you're going to get the same number, so we get x is equal to plus or minus 1. And then those are the values, the critical numbers, that we put on the number line in ascending order from smallest to highest, which is going to break our number line into 3 sub-intervals, from negative infinity to negative 1, from negative 1 to 1, and then from 1 to infinity. And we want to see what the derivative is doing so we can tell what the graph of f is doing. When I decided to choose negative 2 to the left of that number, and I plug it into f prime, if you plug it in here, you get a negative squared, which is a positive, times a negative is going to make that overall value negative. So the red here is the sign of the derivative. And when I plug the 0 in, that's nice because I get a negative squared, which is a positive, times a positive gives me a positive. And then when I plug the 2 in, I get a positive times a positive, which is still a positive. So there's no sign change at x equals to 1. So I'm not going to have a max or min here. I'm going to have no extrema here. But since the sign goes from negative to positive at x equals to negative 1, I can expect that the graph of f is going to have a local minimum at x equals to negative 1. And, you know, depending on what they're asking you, they may be just asking for the x coordinate, so you can state it like I did here. Or they may ask for the critical point on the graph of f. Well, all that means is you just take this negative 1 and plug it back into the function. And when you do that, when x is negative 1, I plug the negative 1 in here and I cleaned it up. I got negative 11. So at the point negative 1, negative 11 on the graph, I would expect to see a relative minimum. Here's another example. So a lot of times I just want to say the sign will go plus minus plus or minus plus minus. They will alternate, but oftentimes they don't. So just keep that in mind. Don't take for granted that because this is a minus, this is going to be a plus, and that is going to be a minus. Sometimes they don't change about a point. So here's another simple example. We've got a function. I took the derivative, set it equal to 0. I could clearly factor out 4x squared, so I did that, and I'm left with x minus 3. So I have these two factors that I have to set equal to 0. So this is 0, and x minus 3 equals to 0 gives me a critical number of 3. I put them on the number line. I chose the test points negative 1, 1, and 4. Very easy and convenient. And I plugged them into the derivative. So when I plug negative 1 in here, I get a positive times a negative is a negative. When I plug a positive 1 in, I get a positive times a negative, which is a negative. So there's no sign change at 0. So I'm not going to have any critical numbers at 0. Any relative or local extrema at 0. And if I plug in a 4, I'm going to have a positive times a positive, and that's positive. So the only sign change I have is that x equals to 3, where the derivative goes from negative on the left to positive on the right. That means the graph is going to go from decreasing on the left to increasing at that point on the right, and so we would expect a relative min. The relative min occurs at the x value 3, and if I want the critical point, or the actual point where that happens on the graph of f, then all I have to do is plug that value into f and evaluate it. Okay, so at 327, I would expect to see a relative min on the graph of f. Now with absolute or global extrema, meaning the very highest and the very lowest point on a graph, or for a function, means the output value, right? It means I plug some number in and get the very smallest number out. So it's similar to the first derivative test where we're going to take the first derivative, set it equal to 0, and find the critical numbers. We're going to use those critical numbers in the interval endpoints. So remember, with absolute or global extrema, they're going to give you endpoints from A to B. And if any of these critical numbers fall outside of that interval, then you discard them, okay? But the idea is we're going to take whatever critical numbers that we can use along with these endpoints and plug them back in. Okay, sorry about that phone call. So I believe I was talking about plugging the critical numbers and the endpoints back into the graph of f double prime, or sorry, f, the original function. And then again, the highest output is going to be the global max, and the smallest output is going to be the global min. So, simple example, we're given a function and the interval. Take the derivative, set it equal to 0, found the critical numbers. Okay. Now I've got x equals plus or minus 1, but what I notice is that negative 1 falls outside of this interval, so I don't have to worry about testing negative 1. Discard it. And over here, I went ahead. So, 1 is the endpoint of the interval, so I don't have to test it twice. So essentially, it boils down to the endpoints of the interval. If I plug 1 in for f, I get a negative 1, and if I plug 3 in for f, I get a 19. So I would say that the global minimum occurs at x equals 1, and the global maximum occurs at x equals to 3. All right, and again, if I wanted the actual points, well, they're right here, right? F of 1 is -1 and F of 3 is 19. So at those 2 points on the graph of F, I would expect to see the highest and the lowest point. Here's another example. I'll bring this in a little closer. Okay, so we've got a function in an interval, took the derivative, set it equal to 0, factored out a 3. This is a easily factorable trinomial, and so we get x equals to -1 and 3. Now, -1, 3 are in the interval, so I've got 1, 2, 3, 4 test points, which is kind of a drag, but it's not too bad. So I went ahead and plugged in both of the critical numbers as well as the endpoints of the interval to get the output values, which are here. Sorry. Okay, so back to this one. So I put in all the critical numbers and the endpoints of the interval, and I looked at my output values, and I see that when x is 3, then y, or f of 3, is -22, so that's going to represent, it's the smallest number, so that's going to represent my global minimum, and the global max is going to occur at the highest output value, and the biggest output value, or positive number, happens to be 10, so at -110 I would expect the global max to occur. Okay, that brings us into section 5.2, applications of the second derivative. So the first thing we talked about was vertical motion, so position, right? We learned that s of t or x of t generally denotes the position function, and that the first derivative of position equals to velocity, and the second derivative of position, or the first derivative of velocity, gives you acceleration. So I believe we did this example in class, or something similar, that a position function is given here, where s of t is measured in feet and t is measured in time. And the first thing they want you to find is the velocity when t equals to 1. So if we want velocity, we have to take the first derivative of this function. So I stated for the greater that the derivative of position equals velocity, and the derivative of that is 3t squared minus 6t. And since I want the velocity at time equals to 1, I just plug a 1 into my new velocity function, and I get -3 feet per second. So again, you're going to have to include your units here. In part B, they want you to find the acceleration when t is equal to 2. Well, we know that the derivative of velocity is acceleration, and since we already have the velocity function here, we might as well take one more derivative real quick to get our acceleration. So here's our acceleration function, and if I want to evaluate it when t is 2, then all I have to do is plug the 2 into my function here for t, and it turns out to be 6 feet per second squared. Again, your acceleration will always be in time units squared, so don't forget that. And then the last question is, when is the acceleration equal to 0? Well, all that means is that you take your acceleration function and set it equal to 0 and solve. So I did that, and I know that when time equals to 1, acceleration 0. In other words, if I take this 1 and I plug it back in here, 6 minus 6 is 0. Okay? So it's really easy to tell. The points of inflection, well, that's where we use the second derivative to figure out where it equals 0 and changes sign. That's really, really important. So you find the second derivative, set it equal to 0, and solve for the critical numbers, just like doing the first derivative test, kind of. And you put the critical numbers on a number line, and you choose test points on the left and the right of those zeros of the second derivative, but you plug your test points into the second derivative because you want to see what the sign of the second derivative is. Why? Because it has to equal 0 and change sign one way or the other. It doesn't have to be from positive to negative or negative to positive. It just has to change sign. So we know back from chapter 2 that when the second derivative is positive, the graph of f is going to be concave up. When it's negative, it's going to be concave down. So the inflection points are going to occur as the sign of f double prime changes, because the only way to go from concave up or down from up is if the sign of the second derivative changes. So here's a function here. I took one derivative, I took the second derivative, I factored out a 12x, factored this down, and got critical numbers of 0 and -1, which I plotted on a number line. And then I took test values of -2, -1/2, and 1, and plugged them into the second derivative because I want to see what the sign of this thing is. When I plug in a -2, I see that I get a negative times a negative gives me a positive. When I plugged in the -1/2, I got a negative times a positive, which gave me a negative. And when I plugged in a 1, I get a positive times a positive is a positive. So these are the signs of my second derivative, and I know when the second derivative is positive, my graph's going to be concave up, negative, concave down, and here it's positive again, so it's concave up. So I know that I'm going to have points, and you don't have to do this, you know, the little concavity things if you don't want to, but it's just to reinforce the fact on the changes in concavity that have to do with the second derivative. But just because the second derivative changes signs at -1 and at 0 on the left and the right, you can just state that points of inflection will occur at x equals to -1 and 0. Another simple example. Oh, and by the way, I put here, you know, if you wanted the actual xy coordinates of those points, all you have to take is your inflection points and plug them back into the, back into the graph of f. And I did that here. F of -1 gives me a -2, so I'm going to expect the concavity to change on the graph of f at -1, -2. And I plugged a 0 in, and if I plug a 0 in here, I get a -1. So at the point 0, -1, I also expect the concavity on the graph of f to change. Another simple example, we have a function, took the first derivative, took the second, and solved, and I only got one critical number. Put it on the number line, which subdivides it into two partitions from -infinity to 1 and 1 to infinity. To the left of 1, I chose 0, plugged it into my second derivative. Plugging a 0 in here gives me a negative number. And on the right, I chose a 2, so if I plug a 2, I get 24 minus 12, which is a positive number. So the sign of my second derivative changes at x equals to 1, so I know that a point of inflection on the graph of f is going to occur at x equals to 1. And again, if you want the coordinates of that point, well, you can just plug in 1 into the original function and get the output value of 3. And then that brings us to the second derivative test, and that's for relative extrema. So you're given a second derivative, maybe a little bit more information, and you don't have a calculator and you don't know what the graph looks like, then you can use this test to find local or relative extrema. So you're going to find the first derivative to get the critical numbers, and then you're going to plug those critical numbers in from f prime into f of x, or f double prime of x. Okay, so you solve f prime of x, set it equal to 0, find the critical numbers, and take those critical numbers and plug them into the second derivative. If the derivative is 0, the derivative will always be 0 at its critical numbers, alright? So when the derivative is 0 at one critical number, and the second derivative, when you plug that critical number in, is positive, you're going to have a relative minimum. And when the first derivative is 0 at some point, and you take that critical number and plug it into the second derivative, and it's negative, then you're going to have a relative max. And if they both equal 0 when you plug that critical number in, then that test, the second derivative test, is going to fail, and you got to go back to the first derivative test. And I did find one in the book that fails, and I don't know if it was a homework problem or not, but we're going to go over it. So, simple example here. Here's my function. I found the first derivative, set it equal to 0, and I found the critical numbers. So, then I took the second derivative, which is just 18x. Now I'm going to take plus 2 and minus 2 and plug them into my second derivative. So f double prime of 2 gave me a positive number, and f double prime of -2 gave me a negative number. So what does that mean? It means that f prime of 2 is 0, because we solved for it, and f double prime of 2 is positive, so that means I would expect a relative minimum on the graph of f at x equals to 2. Likewise, when I put the second critical number in -2 into the derivative, I know that f prime of -2 is 0, and when I plug it in here, I get a negative number, so I would expect a relative max. And the reason why is when the second derivative is positive, we know the graph is concave up, so we're going to have a min. When it's maximum, we're going to have the top of the mountain, so we would expect a max. Here's that one where the test failed. So here's our function. I took the derivative, got the critical numbers. Okay. took the second derivative, which is 30x minus 60x cubed, and the first critical number I plugged in, thankfully, was a 0. When I plug a 0 into the second derivative, it equals 0, so right away it fails. There's no need to even test these other ones here at all. When that happens, that means I got to go back to the first derivative test. So I took the first derivative, we found the critical numbers. So even though you got to go back and use the first derivative test, it's not that bad because you have your critical numbers. At this point, you just need to plot them on the number line and then plug test numbers into the derivative to see where it's changing sign. And as you can see, it changes sign from negative to positive here, so I'd expect a relative min at x equals to 1. Doesn't change sign about 0, so it'd have no extrema at 0, and then it goes from positive to negative at x equals to 1. Sorry, my graph's a little bit off. So we would expect a relative max at x equals 1 and a relative min at x equals negative 1. And that's it. Fin. So I hope you have a good rest of your weekend, and we'll see you on Tuesday.